morning, everyone, and welcome to Barnesden Hall. Welcome to those of you who join us online. My name is Christine Goodfellow. I'm the Academic Program Manager here at Gresham College, and it's my great pleasure on behalf of the entire team to welcome you to our lecture tonight. You know the drill, a few housekeeping rules. If there's a fire alarm, please make your way to one of the two exits as quickly and as calmly as you can, and there will be colleagues waiting outside helping you to find a safe space. After the lecture, we'll have a Q&A. You can either, if you're in the hall, raise your hand and we'll bring you a microphone, or you can scan the QR codes. There are two on the side screens. If you're watching online, there should be a QR code on the bottom right corner of your screen, and then the questions will pop up here on the Slido tablet, and I'll try to mix it evenly between online questions and questions in the hall. It's my great pleasure to welcome back the Frank Jackson Foundation Professor of the Environment, Professor Helen Czerski. Helen is a physicist and an oceanographer and a Professor of the Environment and Society at the Department of Mechanical Engineering at UCL London. Her research focuses on the physics of breaking waves and bubbles at the ocean surface. She's an experienced field scientist. She's actually just come back from a 5-week stint for a field trip. And she has spent months working on research ships in the Antarctic, the Pacific, the North Atlantic, and the Antarctic. She currently co-hosts BBC Radio 4's flagship climate and environment program, Rare Earth, and has explored the physics of everyday life in a range of BBC documentaries. Tonight's lecture is on An Ocean of Air. It's the third in the series called Notes from a Large Planet, A Citizen's Guide to the Earth. So please help me welcome Professor Helen Czerski.
Thank you, Christine. And hello to everyone in the room and online. So, as you heard, this is one of a series of lectures, and the point of this series is to really look at the systems of Earth. So we hear a lot in the news about how the planet is changing, and I think just hearing about all the bad things, it's very easy to feel helpless, right? What can you do about it? It's just a shopping list of bad things. And I think there is enormous value in having familiarity with how those systems work to start with before you start worrying about how they change, because it gives you a sense of agency. So the point of this series of lectures is to go through the great systems of this planet and to hopefully give a bit of perspective on them, sort of how they work to start with, and so to provide some context for the rest of life. And of course, these are fascinating systems all by themselves. And so there's always interesting things to learn. There's always interesting history that goes along with it. And today's topic is the atmosphere. So when we think about exploring, we don't often think about the atmosphere, but I want to take you back to the 1850s and 60s, which was the great age of exploration, certainly in England. There were scientists climbing mountains and exploring deserts and pushing the boundaries in all kinds of ways. So how do you explore the atmosphere, though? You know, it's not, you know, sort of, you can't just walk up a mountain. You can walk up a mountain to get there. People did do that. But to get into the atmosphere, that's not enough. Fortunately, in the 1850s, a solution had been around for a few decades. So hot air balloons had been invented several decades before, actually. And you would think that in the golden age of exploration, the scientists would be out in the hot air balloons, exploring the atmosphere in the same way. But it didn't happen like that. And the reason it didn't happen like that, certainly in England, was because the 1850s and 1860s were known as the era of balloonacy. Because balloons were not there for sober scientists to do serious trips and study things in a very careful way. They were basically there for the vulgar mob to be entertained. Vauxhall Pleasure Gardens, which is not very far from here, was a site of a lot of the balloon launches in London at that time, actually because it was close to the coal works, which supplied the gas that you could use instead of heating the air. And it was basically a drunken party. That's what happened. Eventually, a balloon would go up. A lot of drinking went on. The people in the balloon were not necessarily sober. Everybody was having a great time. And the scientific society in Victorian England was horrified by all of this, by this balloon mania. And so they basically told the scientists, we're not going to fund you to join this bunch here, the party people in the balloon. So you're just going to have to stay on the ground and cope. And the Royal Society actually said at some point that it did not want to fund balloon science because it did not want to encourage balloon mania. But scientists didn't give up. This guy here was interesting, James Glaisher. He was a very well-known meteorologist, a very well-established, serious scientist. And he could see that there was something in this. So he said, the balloon, considered as an instrument for vertical exploration, presents itself to us under a variety of aspects, each of which is fertile in suggestions. His mind is bubbling with experiments he could do if he could just get up into the sky to see the atmosphere. And he's really excited about this. He's saying, within the waves of the aerial ocean, their nameless shores, 1,000 discoveries to be developed if all of us scientists could just get up there. So the Royal Society turned him down, but eventually the British Association for the Advancement of Science said, all right, we'll give you some money. And then the next thing he needed to do was find a balloon. So he did the thing you do, which was go and find a balloonatic. That was what this guy was called at the time, certainly by the popular press. That was Henry Coxwell, and he volunteered to make the balloon that would do what James Glaisher wanted, which was to take him not just a little way off the floor, but up into the atmosphere where he could really do some serious exploration. So they got going, and more or less, this is what it looked like. So this is a stage photograph. They did several flights. We've got the serious scientist on the left here. Henry Coxwell is managing the balloon here on the right, and everything is going very well. And this is so Glaisher, as this was going on, was continually taking notes. He was very careful. There was nothing in any of his notes about enjoying the view or it being pretty or any frivolous stuff like that. He was interested in the science. But his notes are very telling. And it was the third of their balloon flights that became particularly famous. They started going up, all was going well. Glaisher was taking his notes, it's very cold, we're getting very high, covered in ice. Mr. Coxwell pants for breath, so he was apparently part of the experiment, couldn't see to read the instruments. And then he's taking their pulses as he goes as well. And I haven't gone through the notes to see how the pulse rate was changing. But, he's trying to do serious science in some really challenging conditions. So that's how it sort of started off. Sometime later, this is a cartoon representation of how it was going. Now, on the right here, we've got James Glaisher, who is insensible at the height of 7 miles. And the reason they're at 7 miles is that something's gone wrong. What's gone wrong is that there's a valve on the balloon that's got stuck. They can't control the balloon, and so it's just going up. So basically, James Glaisher passes out. Henry Coxwell takes matters into his hands and genuinely climbed up on the outside of the balloon to try and get to the valve that was stuck to fix it all. And the last reading in the barometer before he lost consciousness was 8.8 kilometers up. They were a long way up. And for context, the height at which a commercial airline or transatlantic flight at full altitude is about 10 kilometers. So they had every right to be passed out and cold. Anyway, they came back with very useful measurements. They had measured a profile through the atmosphere. No one had ever been up there, anywhere near. That record stood for a very long time, because no one was going to do that again. But basically, balloon science, excuse the pun, never really took off. So they did this, but basically it was seen as hard to control, difficult. You didn't really get anything sensible done, wasn't proper exploration. And so exploring the atmosphere by actually getting into it just didn't really happen. But at the same time, there was a recognition that, it's easy to ignore the atmosphere in our everyday lives, but there was a recognition that all of this stuff up there was doing something. And actually, so I've got a quote here from Alfred Russel Wallace, who is not the person you might be expecting to comment on this. So Alfred Russel Wallace is the one who came along a little bit later than Darwin, but had some of the same ideas and kind of pushed him to publish. But he had a very illustrious career writing about science, writing about the world, and he was very interested in how the world worked. And in 1903, he wrote this quite extraordinary book. Now, I'm not going to read out too many quotes, but I think these words are really interesting. This vast invisible ocean of air, and I think that's the first time that phrase was used. It's so important that depriving life of it for even a few minutes is destructive, has all these beneficial effects of which we usually don't bother with. And then there's this phrase here, it really is the most complex structure, a wonderful piece of machinery from which the fabric of organic life is compared and renewed. And so he can see what it is, but no one can really go into it to look at what it is. But of course, today we can. Today we do have a different perspective on the atmosphere. We can go into it in various ways and see what's going on. But I really like that bit of history because it's easy to think that because the atmosphere is actually right here, closer than so many other of the extreme environments that we might consider. If you want to go to Everest, it's a very long way away. Whereas the atmosphere is just a mile up there. It's sort of not accessible, but it was deeply mysterious for a very long time. And yet they knew there was something interesting to say. And so now, we're all used to amazing images like this, where we can see that there's this very, very sort of narrow shell on the edge of the Earth, or just a glow on the edge of the planet. And that is this pool of air, this enormous reservoir of air, which looks very thin and very flat when you spread it out over a whole planet. But this is a critical feature of Earth. And so what I want to do in the rest of this lecture is to take you through some of the sort of bits and pieces of how it works, the big picture, not too much about the weather, because you listen to weather forecasts all the time, but some of the fundamental things that are going on to set up what the atmosphere is and how it works. And so there's a little bit about the what, how it interacts with the things that it touches, how it's changing, and then the big picture at the end of it all. So we're going to start with the what. Being a very literal-minded physicist, I always like to know what it is I'm dealing with. So it's very cheerful for me that this all begins with chemistry. So we know this, right? You've probably all learned at school that if we look at the composition of the atmosphere, most of it is nitrogen. A decent chunk of is oxygen. There's about 1% of argon, which went unnoticed for a long time. So that's mostly what the atmosphere is. And then there's this tiny sliver on that pie chart, which opens up into another pie chart, and most of that, and this is everything else, the rest of it. Lots of carbon dioxide on this scale, and then tiny fractions of all these other things. And the thing about this, they're sort of chemical names, and they do different things, but and there's water. There's a kind of, this pie chart is a bit of a cheat in some ways. That's the dry mass. There's also, depending on what weather you're in, what the atmosphere is like that day, there's a varying amount of water. And actually, when you're in a stuffy room, this is why it's hard to breathe, because if it's humid, there's lots of water molecules in the air, and that means there's less space for oxygen. And so basically, the effective oxygen concentration goes down, and it's harder for you to breathe. And that's what it means when you're in a stuffy room. But if you think about how complex our world is, this looks suspiciously simple, right? Think about, some of you might be wearing perfume today. As you walk down the street on the way here, you might have walked past a shop that was selling food and you could smell the food. There's all this stuff that the messy world down here is producing, and it sort of goes into the atmosphere, right? It must do, because our noses are detectors for it. Why is this so simple? That's an interesting question. And it turns out that the reason that the composition of the atmosphere is quite simple is because basically we've got a cleaner. And that cleaner is an oxidizer, which means that it sort of breaks things down by shifting, making things usually into simpler, smaller molecules. So, for example, that turns methane into carbon dioxide and water. And it's this mysterious thing here called a hydroxyl radical. It's basically 2/3 of water, and it's very, very chemically reactive. It lasts for only a tiny fraction of a second, but any sort of organic complex molecules that get hit by this will react with it, and it gradually breaks them down. So this is continually cleaning the atmosphere, along with a bit of ozone at ground level. And so all these other things, these sort of more complicated molecules, eventually get broken down to simpler things. And that's the reason our atmosphere is simple, because it's got these cleaners effectively coming around, simplifying everything by breaking up all the big molecules. And that cleaner is quite good fun. You might have heard the phrase that sunlight or sunshine is the best disinfectant. It's literally true. And the reason it's literally true is the place that this cleaner, this hydroxyl radical, the place it comes from is reactions with sunlight. And so what we're looking at here is a map of those little cleaners. They only last for a very short period of time, but you can kind of work out where they are. And what we're looking at is where they are on Earth. So the redder it is, the greens and reds, that's where these little cleaners are being produced and they're doing the cleaning. And the reason that this spot is moving across the map is because it's when if the sun is shining down on the land and over the ocean, the sunshine creates these hydroxyl radicals. And then they react and they sort of clean up everything else. And then the sunlight moves on. And so basically the sun is like a spotlight that's generating the cleaners that are simplifying our atmosphere and keeping it relatively straightforward. But there are obviously there are tiny traces of lots of things in the atmosphere, but most of them are being continually cleaned out. And of course, it's not just gases in the atmosphere. There are also tiny particles, particulates, aerosol particles, various things. This is a map from a very recent paper of particles in the atmosphere of a particular type, PM2.5. You might hear those spoken about as a pollutant. But of course, not all particulates are pollutants. Quite a lot of them are there naturally. And if you look at the red in the middle there across the Sahara Desert, that's dust. And actually that dust that's blown up from the desert gets carried across the ocean. It fertilizes, when it falls into the ocean along the way, it fertilizes it. And actually it even fertilizes things in South America. And that's an entirely natural process. So some particulates in the atmosphere are really important for structuring our world in the way we take for granted. And it's also the case, well, so let's look at the top. If we look at the top of this here, you can see it doesn't go all the way to the North Pole. It really like this projection really annoys me because it misses off the poles. But if you go right to the top, you can see that the particle numbers, it's getting very blue. The numbers of particles in the atmosphere are getting very, very low, close to the North and South poles. The air there is really, really clean. So naturally, in the sort of these kind of latitudes, in 1 cubic centimetre of air, you might expect maybe a few thousand, say 5,000 tiny, tiny particles in just 1 cubic centimetre. And quite a lot of those are natural. Obviously, pollution adds more of them, but that's natural. But up near the North Pole and the South Pole, that's not the case. That air is a long way from anything that would introduce particles. And so I worked... And just to show you the consequences of that, I worked on a scientific expedition at the North Pole a few years ago in 2018. We were literally sitting on top of the North Pole. That bit was a bit accidental. We went to that area. It happened that the right ice floe was right on the top. And what was weird about working there, so we were living on an icebreaker and then walking out across the ice floes to work and to study that natural environment. And it got really cold, sort of minus 15-ish, although it was during the summer. And the thing that was weird is that you never saw your breath, however cold it got. Like here, you know it's a chilly day because you step out of the door in the morning and you breathe out and there's that really fresh, kind of crisp feel, which is actually because your nose can't detect all the stuff because it's cold. It's not that it's not there. But also, you sort of breathe out and, you see your own breath. That's how, it's a sort of reassuring reminder of why it's cold. But at the North Pole, there aren't enough particles for that to happen. So what's going on here? This is my colleague, that's my hand, and I was holding a thermos flask of hot water at 85 degrees. And what she's doing, she's got a cigarette lighter, and the reason she's got it is not actually because she was a smoker. It's because when you flick a cigarette lighter, it burns really inefficiently, and so it makes loads of tiny, tiny little particles. And so if we play the video here, when she flicks it, suddenly then you can see water condensing. So in order to see a droplet like this, to see what we think of as steam, you need a tiny particle, and then the water's got something to sort of glom onto, and that's when you get particles. So that's when you get visible steam. So if you don't have do that again. So if you don't have a tiny particle to start with, you don't get any visible steam. You don't get clouds, for example. And what we were actually doing there is studying where the particles that do form the clouds come from, because there aren't very many of them. So tiny particles are needed to form clouds. And cloud physics is one of the most complicated bits of how the planet works. But a crucial part of it is what these tiny particles are and how they behave and how they influence clouds. So of course that then, if even natural particles can have an effect like beginning or ending a cloud, sort of getting clouds started, then the pollution that we add into the atmosphere can have an even more significant effect on the weather. And this is a paper that was published within the last year. And the reason they published it is that they were looking at the effect of shipping emissions on the weather. And the reason they were looking at this time is that the shipping regulations changed back in 2020, I think, and the amount of sulfur that you're allowed to have in the fuel globally out on the open ocean went down by quite a lot overnight. So that suddenly the fuel had lots of sulfur and it didn't have any more. Now, in the years coming up to that, scientists had been noticing that where you had lots of ships, you tended to have more clouds and more thunderstorms. And so what this lot did very sensibly is they said, well, we'll watch the transition. We'll watch the years coming up to the fuel change, and we'll watch the time afterwards. And what they were looking for was lightning, clouds and lightning. So these are ship tracks. There's actually no land outline on that. All the coloured bits, the yellow bits are the places where there's the most ships. The purple bits are the bits where there's a few fewer ships. And this is the Malacca Straits. This is one of the busiest shipping lanes in the world. So you can see how many ships are coming and going. And of course, they're burning fuel and they're putting particulates up into the atmosphere. And then this bottom one here is the location of lightning strikes. And you can see that where the biggest the busiest shipping lane is, that's where lots and lots of lightning is. So what these scientists did is they said, well, let's measure how much lightning there is before and after the fuel change, because the particles are changing the clouds. So if you take the sulfur away, sulfur particles are a really good starting point for a cloud. So if you take it away, what do you get? So the lightning decreased by 76% over these 3 years, just because the particulates in the atmosphere had changed. And then 47% across all of the South China Sea. So the point is that there's sort of structure to what's going on, right? Connections that you might not expect can have a really significant difference. And I'm sure people living in that region will have noticed that. So the thing about the atmosphere is it's got no boundaries. You can make some sulfur or some particles, but there's nothing to stop it really getting anywhere, sort of. And so it's worth spending a moment, I think, thinking about how the atmosphere mixes together, because the pattern I just showed you is really clear. But it's really clear because it's very local. It's only in the place where those particles were produced. So generally, if you look across the whole atmosphere, it takes about a year for it to mix up. So gases can travel, they moved around by turbulence and by the winds, and over a year you can kind of average out. All of the atmosphere is the same. In the ocean, you can have a very cold bit of ocean, and then you can travel 1,000 miles and have a very warm bit of the ocean. In the atmosphere, the temperature can change, but the composition won't change. Our atmosphere is generally all very, very well mixed up. So we emit loads of stuff, and as I said, quite a lot of it's cleaned up, so it has a very short residence time in the atmosphere. And just to give you an example of the lengths of time that things typically last in the atmosphere, sulfur dioxide, which is what was coming out of the ship stacks, only lasts about 3 days. So that's why those patterns were so clear in the map. It's because you only see it right where it's produced. But then other molecules like ammonia and carbon dioxide, they last longer and longer, and that kind of smears out the pattern until you get to things like CFCs, which are very well distributed around the planet because they last for a very, very, very long time. So they've got loads of time to mix in. So you don't see very clear patterns in where they are. So the atmosphere is an interesting sort of mixture of very well mixed, and then it has these very local patterns for short-lived species. And one of the things that, so it's just CFCs lasting a long time. So where there's a pattern, we can see it. And there was actually a satellite launched this year pointed at Europe specifically to look for pollutants. So, it's not played? That's going to play. Okay. So Sentinel-4, so Copernicus is a European agency that puts up satellites to monitor everything. And they've put up pollution monitoring satellites before, but they've always kind of moved around the whole planet, so they don't come back to the same place very often. So they sort of scan around everywhere, but they're so busy whizzing over the top that you don't come back to exactly the same place very often. The thing about Sentinel-4, which was launched in July and is just starting to produce proper data, is that it is, let's see if we can play that again. Forward, back, there we go. Is that it's geostationary. It's looking down from one position right at Europe. And so it's the first time that we have had the ability to monitor pollutants. It's there specifically to look for pollutants hour by hour. So the refresh rate is once an hour. And so from the next year onwards, we're going to be able to see this kind of detail. So this is some of the very early data that came from this satellite. And you can really see the sources and how the weather changes, how it mixes around. And so our view of the chemistry from the atmosphere now is really, really good. So we had a lot of chemistry. Let's have a little think about the physics. The atmosphere is really heavy. No one ever thinks that because we just kind of wave our arms around in it. But it is really, really heavy. If you were to, sort of create a column that starts on the ground and just stretches upwards, the weight of stuff that is pushing down on you, because gravity is pulling air in, pressure is kind of pushing it back out, and the balance between the two sets the pressure at where you are. And the atmosphere basically acts like a scale. That pressure is pushing down on the atmosphere. You can weigh the atmosphere by sort of adding up the pressure over the whole surface. But if you were to look at how much pressure it is, it's equivalent to about a column of 10 meters of water or 1.27 meters of steel that is pushing down on us all the time. So the point is that it's not that ephemeral. There's a lot of it, right? It's heavy, it's substantial, it can push things around, it can do things. And actually, one of the most important things it does is make it possible for the ocean to exist. The only reason that liquid water can exist is that it needs to have some gas kind of pushing, it needs to have pressure, basically, otherwise it would all evaporate. So we only have an ocean because we've got so much pressure pushing down that it gives the water a space to exist. And the physics of the atmosphere is basically organized by density. So denser things will be at the bottom, and in the atmosphere, it's generally temperature, a combination of temperature and pressure. So you might have heard of these layers of the atmosphere in the bottom 10 kilometers. That's most of the atmosphere. That's the sort of busy bit. Turbulence is mixing things up. That's where all the weather is. Above that, you have the stratosphere, which is much thinner, much more nebulous, and then it kind of goes up into layers. They are layers, but there's so little there that the density really, really high is very, very small. So basically, this bit of the atmosphere is where it's all happening. But the interesting thing is that 80% of the entire atmosphere is down here, but it has almost all the water. And that's really significant. It's kind of weird that even though the atmosphere is generally well mixed, you don't get water up there. And the reason that you don't get water in the stratosphere is that it's so cold by the time you get that high up that the water freezes and it basically falls out. So it can't get up into the stratosphere. But that lets us do something very useful. Because if water is annoying to you, we do actually have an accessible place to go where there's almost no water, and it's just 12 kilometers up in the bottom of the stratosphere. And I have been there. There was a fabulous plane that NASA had until a couple of years ago called Sophia. And Sophia, this is a modified 747. It's kind of got an extra bulge in the back. When you're standing next to it, it sort of looks like it's about to lay an egg. But the reason for it is that Sophia was an infrared telescope. So they wanted to see infrared light. Water is really annoying if you are an infrared astronomer. It absorbs everything. It basically makes your world opaque. So they hate water. They want to get outside it. So you can either put stuff into space, Or you can go to this very convenient place in the bottom of the stratosphere. And the critical balance is that there is enough air to fly the plane, which is very important, but not so much that it's going to interfere with your astronomy. And so Sophia was modified to take off. It flies up into the stratosphere above the weather, or she did. And then this sort of hatch on the back opens. The telescope is then pointed at the sky. The pilot has to keep going exactly in the right direction, so the telescope is pointed in the right direction. But the amazing thing when you're inside Sophia, so that's kind of in a sealed compartment, but when you're standing in the plane, you can look into that compartment and it's kind of moving. It's sort of bouncing around like this. But what's really happening is that it's correcting for the motion of the plane so quickly that the telescope is absolutely stationary, and it's the plane that's moving because it's correcting for the movement of the plane so fast, so it stays looking at exactly the right place in the sky. So Sophia did fabulous astronomy for 12 years, I think, but it was because there's a place in the atmosphere where you're outside the water vapor, and it gives you access to the universe while still being connected enough to Earth. So the atmosphere is a reservoir, right? We don't think of it like that, but it's a sort of a reservoir with a very, very large surface area to volume ratio, because it's so thin and so flat that even though it's got a massive volume, it's very well in contact with things. Lots of it touches other stuff. And that means there's lots of opportunities for exchange. So what's in and what's out? It's good to start with what's out, actually. So even though this is kind of nebulous, because there's actually quite a lot of mass in the atmosphere, it's really useful at shielding us from things. So keeps the most damaging UV light out because of ozone high up. Mostly keeps meteorites out, mostly. It does keep the energy in, we'll come back to that. And it keeps space debris out. So actually, we do use the atmosphere as a trash can, as a rubbish bin, because we deliberately burn up, when we deorbit a spacecraft, a satellite, basically we want it to burn up in the atmosphere. We want to use that mass in order to heat this stuff up so it just burns away. So even though it's nebulous, it does keep a lot of things out, which is sort of a one-way thing. But when it comes to interactions, the atmosphere is a really, really active place. And so we've got sort of an approximate representation of land and ocean and all the things down here. But it's relatively simple. Things can go from the ocean and the atmosphere up, from the ocean and the land up into the atmosphere. That might be particles, it might be gases, might be water. They can come back down. There's lots of chemical reactions that can happen in the atmosphere itself, so that's kind of going round and round. And then rain. So rain is the other thing that kind of cleans out the atmosphere a bit, that when raindrops fall, things dissolve in them and they carry them out. So you've got this very active thing, chemically and physically, that's putting stuff into the rest of the world and giving it back constantly. So how are we going to study that, right? How do we study that today, having said that it's doing all these things? Because if one thing that's noticeable in atmospheric science, it's that not only are there not scientists in balloons, but there aren't scientists anywhere else really up in the atmosphere regularly. There are research aircraft that fly in the atmosphere, but they're moving, right? Balloons move because they drift. Aircraft move because they have to stay up in the air. No one uses helicopters because their rotors are so disruptive that it just disturbs everything around them. So we're not really very good at getting inside the atmosphere without disturbing it. So what do we do today? Well, what we do today was more or less foreseen, actually. There's a lot of history in this lecture, but I think it's quite fun. This was from 1934, the New York Times. And in their science page, which was sort of one long column about all these different things. And Professor Compton, I'll bring out the quote, who was a Nobel Prize winner, somebody had just had a go at going into the atmosphere and it didn't go very well. And Compton had said, well, surely it would be better if you could organize things so the scientist just got to sort of sit in security and at his ease in a laboratory, rather robots inform him by radio what the findings are. This is 1934. And I think he would have found himself very at home in the world of remote sensing today, right? Because scientists, I mean, I go to sea, but I'm rare in my university that I go sort of out into relatively physically challenging places. Quite a lot of scientists are sitting in security and ease. Not, you know, it lets them do very, very good science, it's fine. It's a lot less fun. But so mostly the problem of getting into the atmosphere is now done by machines of one sort or another. It's not the humans doing it. Now, this is one of the wonderful analog things about the world. One of the things I like about modern science is there's this really good sort of confluence of super sophisticated, computational, you know, amazingly sophisticated stuff. And then just things that are really basic and analog. And this is one of them. So that is a balloon. And if you follow the string all the way down, right at the bottom here, there is a tiny package. And at the time this lecture started today, at 6 p.m., I can tell you with a very high degree of certainty that around 1,200 of these went up into the atmosphere at the same time. And that's because this is what's called a radiosonde. That little package at the bottom, it measures temperature, pressure, humidity, kind of atmospheric measurements. And there is an agreement around the world that these radiosondes are released twice a day, 6 p.m. and 6 a.m., in our time zone, as it happens, but it's the same time around the world. And these little packages, you basically, I've been in the rooms where they do this. They've even let me hold the balloon sometimes. You get given this great big white party balloon, you fill it up with helium, and then you go outside holding it like this, and you tie the little package to the end and make sure it doesn't get twisted up, and then you let it go, you know, like sort of something like a cartoon from Winnie the Pooh. And this thing goes up into the atmosphere, and these balloons are special because they're really, really stretchy. So as they go higher into the atmosphere, they stretch because the pressure around them has gone down. So they go up and they get bigger, and they go up and they get bigger. And it can take them 2 hours to go all the way up through the atmosphere. They kind of get pushed around a lot on the way. They can go a long, long way up. But at some point, it's stretched so much that it bursts. And at that point, the package falls back to Earth. It may or may not get found. Not many of them get recovered. But all the time it's going up, it's sending data back. So this is basically how we ground truth our weather forecasts. This is the only thing really that we do regularly that gets us into the atmosphere to measure what's actually happening at that point. So right now, there are about 1,200 or 1,300 of these things. Slowly, we're 37 minutes in, so, they're probably well on their way up to the top of the first layer of the atmosphere, and they're sending back data right now that will inform the weather models that will tell you the weather tomorrow. So I love how analog this is. It's brilliant. And these are all the locations. There's a fixed number of known locations. And actually, when we were on that ship at the North Pole, once we started releasing our radiosondes, the weather forecasts got better because there was a data point to constrain the model in that area, because otherwise there's just no data, so the model can just go off and do its own thing. Now, these are not often recovered, but if you do want to put something in that package which is an experiment, which is valuable, then you probably want to get it back. And that is a hard job. So a few years ago for a BBC TV programme, I went somewhere where they were releasing a stratospheric balloon with an air sampling thing, so they wanted to get it back. So they let me hold the balloon, and the balloon, off it went. And then we had to follow it in a car for 3 hours through the middle of Texas. And eventually it came down in a forest, because you're tracking it, and you can't see it, you're just tracking where the GPS coordinates. It came down in a forest and got stuck in a tree. So we wandered into the forest, and there was some people randomly in a house in the forest who came out, And the guy went, all right. He went back and got a chainsaw and he cut down the tree. He felt quite guilty about that. But they got the balloon back and they got the samples. This whole thing took a whole day just to get, and they were measuring tiny particles. So they wanted to trap tiny particles high in the atmosphere. And they gave me a certificate afterwards, which was really nice. It's one of my favorite certificates I've ever had this. And you can, I will read the whole thing because it's brilliant. Span the broad Atlantic Ocean to chronicle the perils of those who challenge the demons of the high thin air, has wandered aimlessly through the flora and fauna and dusty roads of the East Texas wilderness, seeking and recovering balloon payloads, puzzled over the strange speech of the colonials, and has faced the terror of the Texas chainsaw with daring and intrepidity. And she is therefore now designated in perpetuity to be a steely-eyed ballooner. How cool is that? Analog science still has its place. These wonderful sort of analog balloons are still bringing back very sophisticated data, but they're still the best way we have of really getting into the atmosphere. People have thought about whether there are ways to make the whole thing slightly more sophisticated. This is one of the only ideas. So this was actually a student project. The student suggested that, well, perhaps you could send up a glider, and then when the balloon pops, you can then control it, and so it comes back down where you want. Basically, the atmospheric scientists aren't really interested because the atmosphere is so well mixed. It doesn't matter whether you're over here or 3 miles to the left. It's kind of all the same. So I don't know whether this is ever going to be a big thing, but at least they're trying. So that's sort of the physicality of the atmosphere. But the thing that the atmosphere really matters for this planet, more actually than almost anything else, is that it's the gatekeeper for light. And that role is the most significant thing that it does. Now, we tend to assume that the light that we see is all there is. We think the atmosphere is transparent. And the reason we think the atmosphere is transparent is because our eyes can see a limited, we can see what we call visible light. And so we assume that's all there is. But actually, that's not the case, even for all humans. So some of you may know that the artist Claude Monet, towards the end of his life, he developed cataracts. And so the lenses of his eyes became cloudy, and he stopped being able to see as well, which is obviously very traumatic for an artist. And this is relatively early on. He put off having surgery for a long, long, long time. And then, so that's where Impressionism comes from, is this painting, actually, that's called Impression Sunrise. That's his work. But then towards the end of his life, when he really had become effectively blind, he was eventually persuaded to have the cataract operation. He had the lens of his eye removed. And the thing that the lens of your eye has in it is a UV filter, which prevents your eye being damaged. And so there was a period after his eye had healed and he'd got a lens to sort of do that job, that he could see ultraviolet light because the back of our eyes can detect ultraviolet light. It's just the lenses filter it out because it's eventually going to damage the back. So even our own bodies are filtering what we can see. But in the atmosphere, that's much more significant. So here's the electromagnetic spectrum. So we've got all the colors of the rainbow. The wavelengths are getting longer towards the right. And so most of us can sort of see that kind of range. For those 3 years right at the end of his life, Monet could see a little bit more. But the point is there is much, much more of the atmosphere. This is one of, so I've forgotten this bit. So Monet started painting in violets after he had the lens of his eye removed because he could see ultraviolet, and he was trying to represent that color in the colors of paint that he had, which were presumably not ultraviolet. So you start getting things like this that are very purpley. So let's look at the visible spectrum. What is it that Earth's keeping in and keeping out? So this is, you can see the visible light there. So it's kind of the same as before, except now we can see all the stuff on either side. Light's coming in, and you can see there's lots of wavelengths that are coming in either side of what we can see. And then sometime later, which this was covered in the first lecture, light goes out in the infrared over here. So you've got light coming in this part of the spectrum and light going out on the right-hand side. And the thing is that the atmosphere is not transparent. But the bits that are important to us, there's bits where light can get through. There's parts of the spectrum which are transparent to light that are known as atmospheric windows. But quite a lot of the rest of the spectrum the atmosphere is opaque. Light can't get through it. So the grey bits here, so this is the same spectrum, the grey bits are where light doesn't get through the atmosphere. So you can see that the incoming light kind of arrives in this little window in the atmosphere where it happens to be accessible to light. And then on the way out, there's this window, and that's what leaves. So the atmosphere is actually quite opaque. It's just that we happen to be able to see in the very narrow part of it where it's transparent. And so it's a gatekeeper for the light that goes in and comes out. And this matters quite a lot. So the light that's coming in is obviously carrying energy. And this is a slide from the first lecture. Because the atmosphere is transparent to light, that light comes in, it hits the surface, it warms up the surface, and then the atmosphere is heated from below, like a hot plate, and the ocean is heated from above. So the fact that the atmosphere is heated from below, that bottom layer warms up, and then it rises, and that's why we have a well-mixed atmosphere, because it's turbulent. It's moving round and round because the atmosphere is heated from below. So that's what gives us big thunderclouds and things. And the ocean has layers because the warm stuff's already at the top, so it stays there. So it's stable in its layers. So the way that light passes through the atmosphere is really, really important. And this is where we come back to the chemistry, because now it's time to think a little bit about how the atmosphere is changing. I want to come back to a historical quote. There are a lot of quotes in this, but I do think this one's relevant. It's going back to Alfred Russel Wallace in the same book. He became what would now be called an environmentalist towards the end of his life. He was very concerned about the state of the world. And this is what he wrote in 1903. So he's talked about the atmosphere, and then he says, and yet it is among those nations that claim to be the most civilized, those that profess to be the most guided by knowledge of the laws of nature, those that most glory in the advance of science, that we find the greatest apathy, the greatest recklessness in continually rendering impure this all-important necessity of life. He is cross. And it's beautifully expressed. We claim to be a people of high civilization, of advanced science, of great humanity, of enormous wealth. For very shame, do not let us say, we cannot arrange matters so that our people may breathe in unpolluted, unpoisoned air. And of course, he's saying this at the height of the Industrial Revolution. The steam engines everywhere. The Victorian world has filled the skies with black smoke and smog. And he is looking at the consequences. But he was enormously eloquent on this. It's actually well worth reading the writings later in his life. He wrote a lot of books. But he had this bang on. This is such a good, it's really stunning. And of course, since then, we have had, the Clean Air Act in this country. People have cleaned up the chimneys a bit, the visible part, but we have not cleaned up the invisible part. So the invisible to us part. So these are some of the molecules in the atmosphere we saw at the start. Oxygen and nitrogen, that one's carbon monoxide. So oxygen and nitrogen make up most of the atmosphere. They are not what we call greenhouse gases, but as we know, there are other molecules in the atmosphere that are. But if you look at them, so what we've got here is carbon dioxide at the top, water, SF6, sulfur hexafluoride, that one's methane. You can see that structurally, just looking at these two categories, there's a difference, right? So these molecules are not greenhouse gases because they don't interact with infrared light. They don't make the atmosphere opaque to infrared light. So infrared can go right through them. And the reason for that is they can't move in any way that would absorb infrared radiation. But all of these molecules here, they can kind of bend and stretch in ways that mean they can absorb infrared light. And so when you have these molecules around, they start to close those atmospheric windows. And we can see that if we look at this plot here. So what we've got are different molecules going up. So the light blue bits are the places where that molecule is absorbing light. We've got the spectrum along the bottom, so we can see the visible radiation. Coming to the right, we're coming into the infrared. And at the bottom, we've got water vapor. So water vapor kind of absorbs quite a lot of bits of the atmosphere. And then carbon dioxide, you can see it makes that bit of the infrared really opaque. And then you can see nitrous oxide and methane. And as you go up, of course, the atmosphere has all of these things in it. And so at the top, that's the pattern that we get. That's where all of these gases are making the atmosphere more opaque in their individual ways. They're closing the atmospheric windows. And the reason that matters is because if light is emitted, if heat energy in the form of infrared radiation is emitted from the surface of the Earth, it travels up, it's about to escape into space. But if there's something that absorbs infrared, because none got in, right? No infrared got in. The atmosphere has already dealt with that. Now we're talking about energy getting out. It gets absorbed, and so it bounces around, and it's as likely to go back down as it is to go up. So there's a barrier to, when you close an atmospheric window, you create a barrier to that energy leaving the planet. That's the deal. And so this is also from the first lecture. The energy comes in sunlight, comes through the atmospheric window that is there. We can measure what comes in. That red is the infrared radiation leaving later. That's what's got through the atmospheric windows on the way out. And because we've added carbon dioxide and methane to the atmosphere, closed the atmospheric windows down, there's now an imbalance on average over the year. And that's what climate change is, the accumulation of energy in the atmosphere because we have closed our atmospheric window. Now, I showed this slide in the first lecture. The number was different, and the reason the number was different, it said 0.5 on the previous one. Someone's done the calculation again, and it's higher, which is not good news. So this is what climate change is. It's because of these atmospheric windows being closed, because the atmosphere is the gatekeeper to light. You're probably familiar with the broad consequences of this. This is where we get to the warming that people talk about in the Paris Agreement, 1.5 degrees C, 2 degrees C. It's about the temperature you reach if you trap extra energy in, and that energy has to accumulate, and the place it goes is heat energy. So it's actually a bit poorly defined. They didn't define their baseline very clearly, very diplomatically. What these numbers mean is that you take some pre-industrial average, slightly negotiable, and then you average the atmospheric temperature around the Earth. And that's if you average that over enough years, because it's a bit spiky as the years go on, so you average over a number of years, and that brings you to a representative temperature, and that's what the Paris Climate Agreement, that's what those numbers, an increase of 1.5 degrees means specifically. And we can see that the global mean temperature measured using this, it bobbles up and down, depends on whether it's an El Nino year or not. Sometimes there's a bit more energy in the ocean, sometimes there's a bit more in the atmosphere. We can see the rise. These are different models done completely independently. They get very, very similar towards the end. And so we're accumulating energy. We know this. Just to finish with, I wanted to show you a little bit of the global carbon budget, which is the bit that links the mechanism that links it all together. So this is an organization that was set up here in Britain. It's a sort of global effort now where they keep track of the greenhouse gases in order to follow. Are they in? Are they how much is being produced? How is it changing over time? And they produced their 2025 report in November, just gone. And so I thought it was worth having talking a little bit about what they said, because it is clearly relevant. And what they said is that the remaining carbon budget to limit global warming to 1.5 degrees C is virtually exhausted. And this is what they mean by that. If you can kind of calculate, if you want to get to 1.5 degrees C, how much carbon can you emit before you get there? How much can you close these atmospheric windows before you get there? So that grey is the stuff that's already in the atmosphere. We're stuck with that. That's gone. This pie chart on the left shows you the amount of carbon you can emit before you get to 1.5 degrees C. And you can see that there's only a tiny bit left, and we're emitting approximately 40 billion tons a year. And so there's not very many years left before you get to 170. That's what they mean by saying it's virtually out of reach. And then if your aim is 2 degrees C, you've got a much bigger slice of the pie left before you get to that point. I mean, we would very much like not to get there. It's a sort of serious point, but I think it's worth making because this is kind of what the atmospheric chemistry and physics is leading up to. This is what it means for the rest of the planet. There is a little bit of good news in here. There was a little bit of good news in the global carbon budget. This is a plot of, it's a bit complicated plot, but so we've got time at the bottom. That black line at the top is the annual carbon emissions. So the problem is it's still going up, right? Which is not good if you really want to make it go, not just go down, but almost go negative, ideally. The good bit of news is in this bit here. So you watch that pink line there, which is China's emissions. You can see it's turning over just towards the end. And the reason that matters is not just that China's emissions are enormous, and of course they're manufacturing a lot of the stuff that the rest of us use, so we outsource our carbon emissions to them. But this turning over is really interesting, and you can actually see it in more detail. There's an analysis by Carbon Brief here. This is just China's emissions, and you can see they're going up and they're bobbling around, basically flat for the last 18 months. So China's economic growth last year was 5%. But its carbon emissions were flat because it's building renewable energy so quickly that it's starting to outpace the growth in its economy. And so it shows it's possible, right? That turning this curve over, keeping the atmospheric windows open in order to keep the planet at a sensible temperature, now we're at a stage where maybe next year China's emissions will go down, right? Which will be the first time so European emissions have been going down for a while, but partly because we've been outsourcing everything to China. But it means that it's not enough. It's not enough to solve the problem, but it's a big moment when that curve starts to turn over. It proves we can do it. So, I'm pretty much out of time. How should we think about the atmosphere? There's all this stuff, there's loads about the atmosphere, there's loads to know. What do we think about it? And I think the first thing is to remember that even though we can't see it directly, even though it's this kind of nebulous thing that we don't think about very often, I think this phrase from Wallace, that it's a complex structure, a wonderful piece of machinery, is worth bearing in mind. It's not just some place called away, where things kind of disappear to and never get heard from again. It's a real thing. It's active, it's dynamic, it's got structure, it's doing things. And it's fascinating in its own right, which is always a good thing. The natural world is fascinating. So when it comes to how we think about it, I think that it is the gatekeeper to the universe, right? The fact that our atmosphere lets light through is the only reason we know the rest of the universe is there. Our interaction with the rest of the universe, including in energy, is almost entirely mediated by light, which is dictated by our atmosphere. It is our largest shared resource because it's so well mixed. Anything we do here eventually affects the atmosphere somewhere else. And so of all the, there's lots of shared resources. The whole planet is a shared resource, but the atmosphere is it's shared very, very quickly. So we have a responsibility to look after it, not just for ourselves, but for the people downwind of us. It is a huge physical influence. You can't see it very clearly on this slide. That's a tornado. And I was in that car. It was a very memorable experience. But it is heavy. It's got physical presence, right? It's clearly doing things all the time that matter a lot in the world. Most of all, I think it's the world's connective tissue. And I think that's the way to think of the atmosphere. There was a book written a few years ago by Sam Keane, I think, called Caesar's Last Breath. And you may have heard this statistic that, on average, if you took the last breath of Julius Caesar 2,000 years ago, each of us are breathing in 1 or 2 molecules of that air even now. The atmosphere is the thing that connects us. And so I think it's worth seeing it for what it really is and looking after it a bit better. Thank you very much.
Thank you very much. Fascinating lecture, especially on a drab, grey day like today. I just like hearing about light, and also the links to Monet and the links to history. I really love that. We've got time for questions, a little bit of time for questions. Shall we start maybe with a question in the hall? Jeff is there, my colleague Jeff. He's going to bring the microphone. Anyone who's brave enough to... Yes, thank you.
Thank you. Thank you for a brilliant, inspiring lecture. So the shipping lanes and the sulfur dioxide and the nitrous oxide that you mentioned, and maybe even China's reduction of coal or whatever, is that enough to maybe make a difference to climate change, global warming, the temperature or energy in the atmosphere for the better? Thanks.
Yeah, so it's not enough, but it matters. And it matters because we have embedded carbon emissions in our lifestyle in so many ways that there's loads and loads and loads of sources, right? And every single one of them has to be brought down and not back. And so every industry that makes progress is an industry to celebrate. Now, there was a lot of criticism of the shipping industry. It took them a long, long time to have emissions regulations. There's a lot of their emissions are in international waters where there's less regulation and almost no enforcement, although satellites are now starting to make a difference to that. And of course, earlier this year, people were hoping to get the shipping industry to make a much bigger step in terms of the fuel it was using, and then that was sort of, they thought they got there, and then they turned out they hadn't quite. So it's slow, but it's in the right direction. And I think that it's really hard to look at some of these plots and not get demoralized, right? Because the numbers are so big. But every single thing that gets better, it counts. So if we miss 1.5, the next target is 1.51, right? It's not like we get to 1.5 and then we all give up until we get to 2 degrees, right? Every single fraction of a degree matters. So I think that's why it matters, that every little bit, it's a little bit less worse than it could have been. And those are going to add up. So it's not enough. But the thing that really gives me, more than anything else, like the great tragedy, certainly of the ocean and also, strangely, of the atmosphere, is that we can't see what's happening in it. In the ocean, we can't see because light doesn't go into it. In the atmosphere, we can't see because we're looking through an atmospheric window. We can't see what's going on. But satellite imagery is making it visible. And as soon as you see things like the Sentinel-4 satellite, and you can see, here is the pollution source, you can see who's getting it downstream, right? People in that city are going to start getting cross because they can see where it's coming from. And I think that sort of thing that starts to make it real, that's when the game changes. So years ago, I pitched programs on the atmosphere, on sort of small-scale atmospheric pollution to the BBC, and it always came down to no, because we can't see it. And what I really wanted was to have some kind of camera or optical thing that would let me sort of show a picture of a car and then image the tailpipe emissions, right? And in practice, that's very hard to do in a humid country. There's all these technical reasons, but that's the thing that makes the difference. And so I think the imaging techniques are the biggest single tool that it makes everybody accountable, and that's really important. So I think there's reason for optimism. Don't give up yet.
Well, talking about future and optimism, maybe a question from online. When shall we start educating kids on what they can actually do to help prevent a further rise?
So I don't have kids, but I speak to a lot of schools and teachers, and I think most people in society would be astonished by what kids are already learning in most schools. So I talk to teachers who are building and people who are developing the resources to help teachers embed climate change in every single subject. So my University College London, there's an Institute of Education that's got a whole division basically working on how do we get climate change into education, into every single subject. It is part of history. It is part of English literature. You can read things that were set in periods that were smoky. You can see the Industrial Revolution happening. How do we embed that in the curriculum? And so it is already happening. And I get so many more emails now from children and young people, and their starting point is, I want to make this better. And so I think kids are already, in this country, getting a lot of education. It could be more, but the resources are becoming available. And actually, the kids are far more aware than their parents quite often. But the thing that's okay, because nagging children make parents change their mind eventually. And so that education filters upwards. So clearly, there's a balance, because climate anxiety is real, and we can't give the next generation the impression that either we did nothing and the whole thing is on them to fix, or that it's so far gone it doesn't make any difference what they do. But they do see it, and they do care, and they do look at the world in a way that previous generations didn't, and they're much more ready to hear that message, I think. So, yeah, I think education is getting better. But we can all do more, and every classroom is an opportunity, right, to change, to help them see that we're all on a journey. We've made a start. We have to go further, but they can be a positive part, even in their local area. Doing something locally is really going to matter, and so I think those messages are getting through. It's slower than perhaps we would like it to be, but it's changed so much that I think. When I was the one kid at school, when I was at secondary school, I was a really shy kid. I somehow persuaded the teachers, and I was too shy to talk, so I don't actually know how I did this. But I persuaded them to give me a notice board on the way out of the main hall, and I covered it in green paper, and I put notices on it for sort of conservation volunteering and news articles about the environment. Everyone thought I was a freak, right? Now, the schools are doing that. Like, that's a mainstream activity now. And that's the enormous change. So yeah, I think education's going in the right direction. And teachers, if you're out there, there are so many resources available. Please look for them, because there's loads of people trying to help.
I mean, as you mentioned, climate anxiety, I think the more you know about something, the more you feel, even in the smallest bit, in control and able to change something in a positive way. Hopefully that will also combat the climate anxiety.
Yeah, and local action. I mean, Friends of the Earth used to have this great slogan, which was think globally, act locally, back in the 80s when I was wandering around with my mother, giving out posters to people that no one was reading, flyers. So I think that thing, if you don't have to worry about the big picture, right, look at your local area. Every room is a room that a decision can be made in that makes a difference. So make that your room, right? It doesn't matter that you can't change the whole country. If you can make your school or your workplace do something better, that matters, and you've made a difference. And that's enough. Like, do your bit, right? And then don't try to take responsibility for the whole thing. Because a lot of these are system things, right? Fundamentally, we need incentives to change how industry behaves, what government regulations are. Those are not things that individuals can change directly. You can annoy your politicians, write letters to them, bug them. You can bug, supermarkets that have too much packaging and all that kind of thing. It's effective, it works, but it's indirect. But people have. Most of us are most of us, right? It's not like there's 3 people in a room somewhere who rule the world. It's really true that even today. So I think that what matters is sort out your own backyard. That's what you can do, and then grow that as it happens. It's all very possible. It feels very possible,
Another question from the hall. There was one on this side, yeah.
Thanks very much for the talk, really fascinating. You've actually prompted this question in the last 30 seconds. One of the points you've made was that visible light comes down through the atmosphere, but what gets radiated back up is infrared. Now, many years ago, probably about 40 years ago, I saw some paper which said, well, if we made all the roads white, all the roofs white, and so on, all these black surfaces we have, we would radiate more energy out in the visible spectrum. It would get out, and we'd be radiating less infrared. And this would be, I think it was claimed at the time, sufficient to reduce the effect of global warming, just simply by changing the window. It's crossed my mind with your comment about your local fix, the thing you can do. Changing, or the next time you replace a flat roof, instead of one of these sort of black asphalt type roofs, one could put down white fiberglass, and locally there's just is this a viable thing? Is there any truth in the concept of if we had enough white roofs, enough white playgrounds, enough white roads, we could actually make a difference bit by bit?
So there's 2 reasons it makes a difference. One of them is that it does very directly get rid of some light, but the other one is that you then don't heat up whatever's below it. So if you're into air conditioning or whatever, fans, you're then using less energy to move the heat you've just moved. It is, so I think it will make a difference. I don't know the exact fraction. It's not going to change the big climate change picture, but I think it could put a significant dent in, especially cities which are warm. You get these sort of heat islands, and it could make an enormous difference to that. So I was looking down on a city in a hot place recently, and it was horrifying how many people had dark roofs. And then I realized that you can actually clean the roof. So a lot of these places do have white roofs. They just don't clean them very often. And then they go dark red or whatever color it is. And then, of course, you're absorbing all the heat again. So there's all these really sort of sophisticated techniques being proposed. It's called solar radiation management. That's the sort of swanky term for it. But I think there is a lot of mileage, both for the comfort of people in those. I mean, it's one of those win-win things, right? Because it makes your own home better and cheaper, and it also might help with it. There's no downside to this. So I don't think it's an enormous fraction, but I definitely think it makes a difference, and it's definitely better for the homeowners, although you do then have to keep your roofs clean. But it is, I mean, it really, in my book, it should be solar panels, right? But anything that isn't a solar panel, definitely, you know, make it white. As long as it's easily maintained. So yeah, it's all heading in the right direction, but definitely useful.
There's another question online in a similar vein. Do you have a view on carbon removal technologies and the role they have to play or not in tackling climate change?
Yes.
Big question, right?
Big question. I think it's somewhere in the list of lectures for next year. It's an enormous topic, but the most important thing to remember about the carbon removal thing is that you can imagine the world as an atmospheric time machine, right? Where every year we emit another 40 gigatons of carbon dioxide, and that's going to warm. It's going to sort of warm us up for the future. So you can think of carbon removals as being like a time machine that brings you back in time. So you've gone up the curve for a year, and then if you do some carbon removal during that year, you might be able to come back a little bit in time. And this is an idea that was written about by David Ho. And so there was a big Nature opinion piece that got a lot, that set this out very nicely. So every year we go 40 gigatons forward. The question is, how much back in time for each year could carbon removals take us? And I can't quite remember all the numbers, but if you planted a tree for every person on Earth, so we're talking 8 billion trees, and you let them run for 20 years, they will take you back a year of emissions forward. That massive number of trees takes you back 13 minutes. So the DAC plants in the US, I don't know what's happened to them now, given the current political situation, but Biden funded direct air capture plants that were supposed to remove 1 million tons a year. I think that takes you back 3 minutes, and they can't even make them work yet. So the first very, very strong message on carbon removals is that they are not a compensation for emissions. It is absolutely, it's kind of morally bankrupt, in my view, to claim that offsets are sort of a solution, right? Because if you have an offset, that should be used to reduce the emissions we can't shift, right? It shouldn't justify extra emissions so that you can then claim them back. If you can remove that, then don't do the emitting and still bring it back, right? That's the way to go forward. So basically, carbon removals with all known current technologies will make a tiny difference. It is very expensive. It is very invasive. It may well be that is our last best chance. We need to do the science now to work out how and whether it might work. It would have to be government funded and not funded by, startup culture just doesn't work for this because the incentives are all wrong. But it absolutely does not allow you to continue emitting. So you have to get rid of the emissions. You have to you have to stop emitting. You have to stop emitting. No amount of carbon removals is going to compensate for that. It may be that after we've stopped emitting, we can sort of do a bit of cleaning up, but we can't see it as if we invent carbon removals, we can just keep emitting. Which makes it very depressing that the vast amount of funding that has gone into carbon removal so far is oil companies and companies that are focused on consumption, because they want to say they're carbon neutral. So some science is getting done, so that's good, but it's not going to solve the problem because of the time machine thing.
Thank you very much, Helen.
Rant over.
No. I think we're a bit over time, so I think we have to leave it here. But thank you very much. Helen's next lecture is on the 23rd of March, which is a Monday. So those of you who are used to Thursdays, it will be a Monday, 23rd of March, on A Living Planet. And we're looking forward to that. Thank you very much for tonight.
Thank you.